fundamental theorem of calculus. That's the name of it. There's actually two fundamental theorems. There's the first fundamental theorem and the second fundamental theorem, depending on the textbooks you use. But the fundamental theorem of calculus we're going to talk about, and I do think it's one of the most useful ones, it says that if f is continuous on a closed interval, meaning it includes both a and b, and f, the capital F, is the antiderivative of that. Okay, so f would be something we've done, and then when we do the antiderivative, it becomes capital F. That's how they're going to use that notation of f on the interval a to b, same interval. Then it is the integral, so that curvy thing, from a to b, which means it's from the left endpoint to the right endpoint of lowercase f of x, which is the original function, that is equal to capital F of b minus f of a, meaning this is the antiderivative These are both antiderivatives with those limits of integration is what those are called, plugged in. Okay, and it's plug in top minus plug in bottom. There he is. Welcome. Let me share the screen with you, sir. Okie dokie. Make sure he can see that. There we go. All right. So lowercase f is for the original, uppercase f. So it's saying the antiderivative of a function is equal to, if I'm doing definite, meaning limits. So if you're doing indefinite, that's when you put the plus c. And I'm doing definite, that means there's numbers for those limits on top and bottom here and here. Okay, if you have those, then once you have your antiderivative, you'll plug the top number in minus plug the bottom number in every time. Okay, so we'll try some. Okay, so first one is the antiderivative from 1 to 2 of x squared minus 3. So keep in mind, antiderivative means we're doing the opposite of a derivative. We're taking it back to what it was before it was derived. In general, if it was a trig function, we had to memorize what the antiderivative of that was. And if it was a function kind of like these, we added 1 to the exponent and divided by that number, or multiplied by 1 over that number is the equivalent of. So I don't know, that was a week or so ago that we did that. So if I do this, we're going to work on notation, which is how we write it. I'm going to antiderive x squared first, which means I'm going to increase the exponent by 1. And I'm going to either divide by that exponent or multiply by 1 over that exponent. Okay. So there's the antiderivative of x squared minus 3x, because keep in mind, that's 3x is 0. So if I increase the exponent and divide by that exponent, it's just 3x. Okay. Now, normally, if it was indefinite, I'd put plus c. But since it's definite, I put a bar like this, and I put my limits of integration for what I'm evaluating it for, like that. Okay. That is one notation you'll see. Now, those of you that are going into a math-based field, sometimes you might see it like this with your limits of integration. Okay? Where they'll put it in brackets instead of parentheses with a bar. Those will be interchangeable. Now, what that means is I will now go plug in my top number minus plug in my bottom number. So I will do 1/3, plug in 2 cubed minus 3 times 2. I'm going to put that whole thing in parentheses, minus plug in 1. If you have a calculator, go ahead and type that in. If you don't have a calculator, probably get one out and type that in. Or if you want to do your common denominators and all that in your head, by all means. And you should get a number. I mean, it's going to be a fraction, but. I got negative 2/3. So the process is what we were doing just a little bit ago, where you do the antiderivative. The difference is now we don't have plus c. We just plug in values and get an actual finished value. What's cool about that is the connection between what we were doing last section and what we're doing this section is if it had said find the area under this curve between 1 and 2, it's negative 2/3. Okay. Or it'd be 2/3 because area is positive, but that's the concept. All right, I'm going to erase a little bit just so, because it ran over in here. All right, so we're doing the antiderivative of this. I'm going to rewrite this as that for the sake of it'll help me add in my head. You don't have to do that, but I think that'll help me. All right, so the antiderivative of 3x to the 1/2 is going to be increase the power by 1. So that'll be 3/2 instead of 1/2. And then you divide by 3/2 or multiply by the reciprocal. So I'm going to have 3 times 2/3, which is just 2. Does that make sense what I did there? I did 3 divided by 3/2 technically, which multiplied by the reciprocal would leave me with 2. Okay. And then instead of plus c, I will evaluate it from 1 to 4. So then at that point, you'll go plug in the top number minus plug in the bottom number. Now, if you were doing this without a calculator, this would be a great problem that would make you think you couldn't do it without a calculator, but you definitely can, because that 3/2 power is a square root that's been cubed. So if I square root 4, I get 2, and then I cube it, I get 8, and so I'll get 16 for that first term. Square root 1, and I get 1, and I cube it, I get 1, so I get 16 minus 2, so I get 14. So although it looks complicated because it has rational exponents, it's really not that bad. So we will get 14. Which, if you think about the shape of this graph, it's something like this. We can't geometrically do that area, but we just did the area using calculus under that curve, okay? Because what that does is sums up infinitely many rectangles for us, is the integral does that. Okay, next one. So this is one that requires memorization. You have to memorize what the antiderivative of secant squared is. Anyone by chance have that one done? Or maybe think backwards. What has a derivative of secant squared? Because you guys did have your derivatives pretty well down at one point. Some of you are on the fringe of it, I can see. Okay, it's going to be tangent. Okay, so tangent x is the antiderivative of secant squared x because the antiderivative of secant is tangent. Okay, or secant squared is tangent, and tangent is secant squared. And then we're going to evaluate it still from 0 to pi over 4. And I'm going to say this, and I feel like I'm just repeating myself over and over again, but it's really important. If this did not have limits of integration, you would have a plus c. Okay, but since it has limits of integration, we'll plug it in, and we get a complete value for it. It's very specific. All right, so I will do tangent of pi over 4 minus tangent of 0. And there's that unit circle that you learned last year in pre-calc, and we've done this year, and we keep doing little snippets of it. We don't do a whole bunch at one time. So if you think of your unit circle, pi over 4 is a 45-degree angle. It's here. It has the ordered pair of root 2 over 2, root 2 over 2. That's because it's an isosceles triangle, 45 degrees, 9 degrees. That's why those two measurements are the same. So when I have tangent is sine over cosine, which I'm going to have root pi over 2 over root pi over 2. So tangent of pi over 4 is 1. Okay. Minus tangent of 0. This is 0. That ordered pair is 1, 0, which is cosine over sine, which is 0 over 1, which is 0. Okay, so if you need to write, actually, let's root 2 over 2 over root 2 over 2 is actually what that is, and 0 over 1, so that you have all the steps. So we don't skip anything, but that is 1. Okay. Any questions on that? So tangents is one of my favorite underused trig functions because often they use it with pi over 4, which is a 45-degree angle, which is easy to do. So, any questions on definite integrals? Plug the numbers in. For some reason, I like these better than the indefinite ones, even though it's slightly more work, because it's actually a complete number instead of an equation with C at the end. It feels more finished than the other ones. Okay, if there's no questions, move on to my next slide. Okie dokie. So this is one we could actually probably do geometrically because we're going to have that V shape. It's going to end up giving us either a trapezoid or a triangle. We could do that. However, we can do it without a lot easier or just as easy. And what I do is when I think about this shape. So since it has that -1, okay, it's not centered at 0 anymore. Okay, so when we did the triangle before, it was centered at 0, is no big deal. We need to figure what it's centered at, which is mean where's its x value going to be at. So if we solve this here, I'll get x is equal to 1/2. And so that means to 1/2 of that, something happens, or to one side of the 1/2, something happens, and to the other side of 1/2, something happens. Okay, it's going to have that shape. And so essentially what that does is that makes it into a piecewise function that I will use positive 2x minus 1 whenever x is greater than or equal to 1/2. And then I will use negative 2x minus 1 whenever x is less than 1/2. Or the equal to part can switch. It just can't be on both. Okay, it has to be on one though. But so that's what the absolute value does, is it fills that in for us. So we're just going to do two different integrals. So I will do the integral from 0, because we're starting at 0, to 1/2 of negative 2x plus 1. I'm going to go ahead and distribute that, dx. And then I'm going to add it to the integral of the other part of it, which is from 1/2 to 2. And again, I'm getting those values from here and where we split it. Okay, that's where I'm getting those numbers. You have to write it with dx. Okay, when you integrate, you're integrating a differential. So you have to have that dx on there. All right, we can do that pretty easily though. What is the antiderivative of negative 2x? So increase the power, divide by that power. What do you get? So the current power is 1, so my new power will be 2, and then I'll divide by 2. So negative 2 divided by 2 is just negative 1, okay? And the antiderivative of 1 is just 1x, good. And then we'll evaluate it from 0 to 1/2 in a second, plus the antiderivative of 2x is increase the power, divide by that power, x squared. And then minus the antiderivative of 1, which is x. Good. And then we'll evaluate that from 1/2 to 2. So then go ahead and we'll plug in our numbers. So we will have negative 1/2 squared. The negative is not being squared, plus 1/2. And then if I plug in 0, I'm just going to get 0. So I'm just going to put minus 0 for that whole section, because top minus bottom, I'm going to have 0 squared plus 0 is still 0. And then I will do the other one, which is going to be 2 squared minus 2 plus, I'm going to use extra set of parentheses, 1/2 squared minus 1/2, not plus, it should be a minus. Oh no. Okay. There you go. All right, so I'm going to simplify. Let's simplify this set of parentheses first. So we'll have negative 1/2 squared, but the negative's outside, so it'll be negative 1/4. And then negative 1/4 plus 1/2 is 1/4. Okay. Minus 0. Then we'll have 2 squared, which is 4, minus 2, which is 2. And then 1/2 squared is 1/4. Minus 1/2 is negative 1/4. And we're minusing a negative 1/4 So we're adding 1/4. So I'm adding all that together, 1/4 plus 2 plus 1/4. So 2.5. So it's 5/2. You could type that in a calculator. I just feel like fractions sometimes are better in your head because sometimes we type them in wrong. Any questions on that process? You wouldn't necessarily make a piecewise unless they gave you a piecewise or it was an absolute value, okay? So just keep that in mind. Or they might give you sections, like from here to here, it works with this, and from here to here, it works with this. That would be an example of piecewise. Okie dokie. Second fundamental theorem of calculus. This is my favorite because it's really more like a duh property. Like what it's saying is if I derive the antiderivative, I just get the function. Because you start with a function and then you antiderive it and then you were to derive it, it takes you back to exactly where you were. Okay, that is what this says. Okay, now it does talk about your limits of integration a little bit, and it makes sense to me. If I were to do the antiderivative of f of t, I'm going to get f of, plug in the top number, which happens to be x, minus plug in the bottom number, which happens to be a, but f of x with x plugged in has variables. F of a is a constant. A does not have variables. It's a number. So then when I derive it, I'm left with regular f of x. There's no a because the derivative of a constant is 0. And so I don't know if you can follow that line of thought, but that's one of the reasons that it doesn't deal anything with the a is because you derived a constant. Okay, it'd be gone. All right, so there's that. So I called the duh property because the derivative of an antiderivative should be the original. That'd be like multiplying by 2 and dividing by 2, and therefore it's just whatever it was before you multiply by 2. That's that concept. All right, so we're going to do 2 of these. One easier than the other. So with the duh property, it works easiest if you have any constant as your bottom lower limit of integration and just a linear term for your upper limit of integration. Because like look here, it's just x up here. Okay. So when it's just that variable, it doesn't have to be x specifically, but whatever that variable is, if it's just that variable, it just is what it is. Like this is the square root of x squared plus 1. What reasoning? And they do want you to explain it, and the AP test expects you to say by the second fundamental theorem of calculus. And you have to say of calculus because a lot of branches of math have their own first and second fundamental theorems. There's a fundamental theorem of algebra too. Okay. Watching our time. Find the derivative. So now look here. The bottom number is cool. We're good with that. It's a constant. But the x, that top number is not just x, it's x with an exponent. Okay, so that's a little different. So we're going to have to work a little hard. So my goal would be to make it look like the second fundamental theorem of calculus with some plain term at the top, like just a linear exponent of 1, coefficient of 1 term. So what I'm going to do is let's let u equal x cubed. Okay. We will let u equal x cubed. Okay, so this is going to get a little funky, and it's going to get a little funky fast. So what we're going to do is where it says find the derivative of this function. Okay, so we are going to find it that means it's telling us to do this. Well, that's not equal, but this is what it's telling us to do. Okay, so we're going to kind of do that, but what I'm going to do is because I've now manipulated my x into being a version of u, I'm going to have to manipulate all the x's to be some form of u. So do you see that dx? I need a dx. I don't have a dx. I don't have anything that goes there. Okay, I can't have everything be x's. I need everything to be turned into u. So what I can do is let's do the differential of u. Okay, if you remember, we did that last chapter. Yes. And the derivative of x is 3x squared dx. Remember doing that? So we did the derivative, but instead of doing du over dx, we multiply the other side. Okay, that's really important. So what we're going to do now is we're going to start plugging things in. So I am now going to be taking the derivative with respect to u of pi over 2 to u of cosine t dt all right, and I'm going to then multiply it by, this is a manipulative thing, and I'll explain it in a second, du over dx, which is actually the derivative, not the differential. We didn't need the derivative or differential, we need the derivative. Okay, so real quick, why we have to do that, and because it makes it not change, is if you look at this, do you see I have d over dx? Look at this, du on bottom, du on top, d on top, dx on bottom. So if I have du over du, that simplifies to be 1, and I still have my d over dx. It is exactly the same thing it was before, but I've manipulated it now that when I plug in everything, I can actually use this. So we will do just this part, uses the second fundamental theorem of calculus. So that'll be cosine u. Okay. But then I have to multiply it by du over dx, which is 3x squared. That's what we found here. All right. You don't want to mix variables with u, so we will go ahead and resubstitute back in my u here. So I will have cosine of x cubed, and it's going to kill me to write that 3x squared after it, so we're going to put it in front. It doesn't have to be. The textbook writes it at the end, but I prefer it in front because I don't want to accidentally think there's other stuff inside that cosine. So yes, please ask questions.
Is it cosine still?
Yes, because we're deriving an antiderivative. If you were just deriving cosine, that'd be one thing, or if you were just integrating, that'd be one thing. But because we're mixing those, it doesn't change it. That's a good question. So anytime this is not just plain x or one single variable, you're going to have to do this. It's called u substitution. Okay. And you're going to have to do that. Any questions on that? It's not too hard. It's just not be something you would think of initially until now. You know, that's how you do it. All right. We still got some time. Let's go on. Net change theorem should look really familiar. The net change of something it's talking about if your first derivative is the rate of change, which it is. Okay. Then the definite integral of that is your net change, basically your change overall. Okay. You put it all together. Okay. So think of net, it's putting it all together. Think of adding. When integral is adding, remember the integral is your sum. When your rectangles go to, like, you get infinitely many rectangles, you're adding all those up. So net meaning adding together. If you think of like your net pay or something like that, putting it all together, that's what it is. So I want to do, this is really important for your AP test. There's going to be two types of problems that they will have you do, and they'll use language that doesn't say, please take the derivative or please take the antiderivative. They won't say that. What they will say is rate of change, and we know that to be, why is it skipping my letters? Derivative, right? And then anytime they say accumulation of change, think of adding or net change. They won't just always use this language of net change. Sometimes they talk about accumulation of change, which makes sense that you're adding up a bunch of derivatives, okay? Accumulation of change is your integral. And I say that because there's a wonderful AP problem that we're going to do when we finish all of our notes and we start preparing for the AP test that talks about snow accumulation on like a ski lift like slope. And so much is melting, so much is accumulating, and we get to use the integral for that, and it's wonderful because it adds up all that stuff. So think of this as being an adding. Integrals add, okay? You're summing things up. So then let's do some accumulating. All right, so we have a chemical flowing into a storage tank at a rate of, key term, rate, meaning it's already a derivative, correct? Okay. So a rate of 180 plus 3t liters per minute, where t is number of time, and it gives us a domain for that between 0 and 60. Find the amount of chemical that flows in the tank during the first 20 minutes. So it's asking us to put all that amount in across 20 minutes, okay? So what that is saying is I'm going to sum up all the time, all the amount flowing in between time 0 and time 20. I'm adding up all that rate of change. How you add up all that rate of change is you integrate the rate. You need to always put these in parentheses and put d, whatever your variable is, too, because it is a differential. Okay. Do you see why we did 0 to 20? Okay. So that's what's talking about net change. It's talking about all of the chemicals flowing into that time. You're putting it all together. Okay. So that's why you're going to integrate. So they didn't tell us to integrate. We just have to read and know we need to integrate. And I think that's sometimes the harder part. All right. So what is the integral of 180? 180t. Good. Remember, think of that as t to the 0, increase the power by 1. Okay. Then what is the antiderivative of 3t? Increase the power by 1 to be t squared and divide by 2. So let's write it as 3/2. Okay. Evaluated from 0 to 20. So now we go plug in 20 minus plug in 0. Plugging in 0 will be great and easy. So we're really just going to be plugging in 20. $20 squared is 400. So we will have 3,600 here. We will have 600 here. So 4,200. It says find the amount, so it'll be liters. Okay. Any questions on that? Okay. See if we can finish this last one. If not, we'll finish it tomorrow. All right, so we have velocity of a particle moving along a line, and they've given us an equation for that velocity where t is time in seconds. It says what is the displacement, okay, of the particle on the time interval. Think of displacement as in distance, how much it's moved. It's been displaced by a certain amount, okay? But displacement is positive, okay, always, because distance is always positive. So think about that as well if you displace. So we'll kind of have to watch for signs on that. All right, so it's given us velocity, and it's talking about position. So do you remember when we did derivatives, we started with position. The derivative of position was velocity. The derivative of velocity was acceleration. So if you think about it, I'm going the other direction. So if I have velocity and I want position, I need to antiderive it. Okay. So for A, we're going to have to do the antiderivative of t cubed minus t squared plus 29t minus 30. Nope, minus 20, because I can't read. dt from, and it tells us the interval. When you write left to right on your interval they give you, you're going to do bottom to top. Because remember, if you switch it, it changes the sign, like we learned in a previous section. All right, so let's go ahead and do the antiderivative of that. So the antiderivative of t cubed would be, any ideas? Increase the power by 1. Very good. 1/4 t to the 4th, good. And then antiderive 10t squared. Very good. 10/3 t cubed plus antiderivative 29t. Good. So 29 halves t squared. And then antiderivative of 20t. Put this in parentheses. And we're going to evaluate it from 1 to 5. So that means you are going to plug in 5 minus plug in 1. So you will have 1/4 times 5 to the 4th minus 10/3, 5 to the 3rd plus 29 halves, 5 squared minus 20 times 5. Then minus 1/4 minus 10/3. That's easy to plug in 1. And I have done this one for you, so you don't have to go plug it in your calculators. But just when you do that stuff and he plugs in your calculators, be very careful. And you will get 32/3. So then B is asking for total distance traveled from 1 to 5 of the particle, and that's what we're doing. And so there's a difference between displacement, because displacement accounts for the negatives, and you'll actually subtract the negatives, and because displacement will give you some direction. So I said it didn't have a negative, but it could have a negative in sign. But total distance would mean it doesn't matter if I went forward or backwards. You're still going to count my distance that I actually traveled. So if you're walking in a straight line, you're walking back, displacement would show you didn't move at all. But if I'm walking forward, walking back, my steps would count it. And so we'll wait and do B tomorrow, and we'll finish it up then. But just keep that in mind.